Hey everyone, in this video I want to provide a bit more explanation and guidance for the prime factoring question on this week's homework. So at a high level, this question is still about counting. It's about counting how many prime factors n has, where n is some natural number, and remember natural numbers are just positive integers, starting from 1. So we're trying to determine how many prime factors n has in general. And the way that we're going to do it involves prime factoring n. Or in other words, it involves writing n as a product of prime factors. So let me show you a little bit more about what's going on here. So as the question mentions, the fundamental theorem of arithmetic states that we can write any natural number bigger than 1 as a product of prime factors. Let's look at a few examples. So 48, it turns out that I can write this as 2 to the power of 4 times 3. And now here, 2 is a prime number, 3 is a prime number, so I've written 48 as a product of primes. I happen to use the number 2 more than once. I used it 4 times, but that's okay. Similarly, 72, that's 2 to the power of 3 times 3 squared. Because 72 is 8 times 9. Here's your 8 and here's your 9. Again, I've written it as a product of primes. We can continue. 30 is 2 times 3 times 5. So, 120 would be 2 cubed times 3 times 5. And 600 would be this with a 5 squared. And so on and so forth. So we can prime factor really any positive any positive integer. And I'm telling you that there's a way that we can use this representation as a product of primes to determine how many factors n has. But first, let me show you how to actually compute the prime factorization of a number, because for these 3 examples, 48, 72, and 600, it seems like I just came up with them magically. There's a systematic way that you can sort of determine the prime factorization of any number. And let me walk you through it. Let's use 600 as an example. The way I like to do it is by writing this sort of vertical line here and putting 600 at the top right. What I want to do is repeatedly find the smallest prime number that is a factor of n. In other words, I want to find the smallest prime number that evenly divides n. What's the smallest prime number that evenly divides 600? Well, that's 2, right? So I'm going to put a 2 here. And what do I get when I divide 600 by 2? Well, what's left is a 300. I can repeat this again. What's the smallest prime factor of 300? That's 2. I divide it out and I get 150 left. What's the smallest prime factor of 150? That's still 2. But when I divide 150 by 2, I'm left with 75. Now 2 no longer divides 75, so I've sort of exhausted all of my factors of 2. But 3 does divide 75 evenly. So when I divide 75 by 3, I get 25. Now the smallest prime factor of 25, that's 5. So I'm left with a 5 after that. The smallest prime factor of 5, that's just 5. And now I'm left with the 1 here. And once I see a 1 in this right column, it means that I am done prime factoring my number. So I can just go here and read off this product. And this is a way of writing my number as a product of primes. So in this case, it's telling me 600 is 2 cubed times 3 times 5 squared. Now note that the fundamental theorem of arithmetic states that there is only one way to write every natural number as a product of primes. So there's no other way using a different number of 2s and 3s and 5s or different prime factors altogether to write 600 as a product of primes. Okay, so that'll be important. So now I know how to prime factor a number. So you have the example that's in the worksheet and you have the example here. Now the question is, how can I use this to determine how many factors my number has? So again, let's continue with the example of 600. So how many factors does 600 have? Now remember, if k is a factor of 600, what that means is if I take 600 and divide it by k, the result is an integer. So, for example, like 4 is a factor of 600 because 600 divided by 4, I get back 150. That's an integer. Whereas, say, 13 is not a factor of 600 because when I divide 600 by 13, I get something that involves, a decimal. Meaning 13 doesn't evenly divide into 600. It's not a factor of 600. So I'm trying to determine all of the factors of 600. And of course, I'm looking for a way that's better than just, sitting there saying, okay, 1 is a factor, 2 is a factor, 3 is a factor, 4 is, 5 is, 6 is, 8 is, so on and so forth. I'd be sitting here writing for a long time if I just started counting up from 1 and saying, okay, is this number a factor of 600 or not? And, you could think of other, slightly faster ways of doing this, but there's a systematic way that involves the prime factorization that we just came up with. So here's the key insight. Again, we have this. Any number that is a factor of 600 needs to evenly divide 600, meaning it needs to only be made up of 2s and 3s and 5s. Right? If I try and take a number that has a factor of, 7, automatically you know that it's not going to be a factor of 600 because 600 has no factors of 7. So if you go and try and take this representation and divide it by 7, it's definitely not going to be an integer. But if I instead take this representation and divide it by, say, like 2 times 3, well, we know the 2 and 3 on the denominator are going to cancel with some of the 2s and 3s in the numerator, and the result will still be an integer, right? I could also, change this to a 2 squared, and, I could change this to a 5 squared. And you can see that the result here would still be an integer. So already we know that any factor of 600 has to be made up of only 2s, 3s, and 5s, meaning if we prime factor a factor of 600, it should only be a product of 2s, 3s, and 5s. But that alone is not enough, right? Is 2 to the 4 a factor of 600? No, right? 16 is not a factor of 600. Notice if you try to do this division, you get 75 divided by 2. That's not an integer. So 2 to the 4 is also not a factor of 600. So not only do factors of 600 have to be made up of only 2s, 3s, and 5s, they have to be made up of between 0 and 3 2s, between 0 and 1 3s, and between 0 and 2 5s. Let me make a little bit more explicit what I mean by that. So again, we have 600 is 2 cubed times 3 times 5 squared. I have 4 options for the number of times I'm going to multiply 2 to come up with a factor of 600. Right? I could have 2 to the 0, 2 to the 1, 2 to the 2, or 2 to the 3. Right? Those are 4 options. Okay. Separately from that, I have 2 options for the number of times I'm going to multiply 3 to get a factor of 600. Those options are 3 to the 0 and 3 to the 1. Lastly, I have 3 options for the number of times I'm going to multiply by 5 to get a factor of 600. Those options are 5 to the 0, 5 to the 1, and 5 to the 2. And so you can think of the task of finding a factor of 600 as picking from one number in each of these columns. Right? So I could pick 2 squared times 3 times 5. I multiply those out, I get 4 times 3 times 5, 60. That's a factor of 600. I could also say, go to 2 cubed times 3 to the 0 times 5 squared. Well, that's 8 times 25. That's 200. That's also a factor of 600. So to come up with the factor of 600, what I do is pick one number from each of these columns. And so now this looks a lot more like the counting questions that we are used to, right? Where we have a number of options for the first thing, a number of options for the second thing, and a number of options for the third thing. Right? How many options do I have for how many 2s I use? 4. How many options do I have for the number of 3s I use? 2. And how many options do I have for the number of 5s I use? 3. So that means the total number of factors of 600 is 4 times 2, that's 8, times 3 is 24. So that means 600 has 24 factors. And that's it. We can look at another example. So let's come up with another number, say 1,440. I want to determine how many factors 1,440 has. So let's start by prime factoring it. So we could, proceed with the same method that I told you about before, but there's also a shortcut. If my number ends with the 0, we know it has a factor of 10 in it, and 10 is just broken up into 2 times 5. So right off the bat, I can take out a 2 and a 5, and when I do that, I'm left with 144. Okay, great. Let's continue. 144, that's divisible by 2. When I do that, I'm left with 72. That's still divisible by 2. When I do that, I'm left with 36. Still divisible by 2. When I do that, I get 18. Still divisible by 2, I get 9. And 9 we know is 3 times 3. Okay, we can write it like this if you want to be concrete. And so now I just have to read off this column to get my representation of 1,440 as a product of primes. So how many 2's do I have? 1, 2, 3, 4, 5. How many 3's do I have? 1, 2. And how many 5's do I have? Just 1. Okay? So that means the number of factors of 1440, you notice I have 6 options for the number of 2's that I include. But that's just the exponent on 2 plus 1, right? Because it's anything from 2 to the 0 to 2 to the 5. And so 0, 1, 2, 3, 4, 5, there are 6 options. There are 3 options for the number of 3's I include, but that's just 2 plus 1. And there are 2 options for the number of 5's I include. Again, 5 to the 0 or 5 to the 1. Well, that's just 1 plus 1. So this is 6 times 3 times 2. That's 36. So this is saying 1440 has 36 factors. So the twist that we introduce in part B is that we ask how many factors does a number have that are multiples of some other number. And so the way to think about this twist is as if it reduces the number of options that we have for each of the prime bases. In this case, if we're using 1440, our prime bases are 2, 3, and 5. Okay. So for example, 2 squared times 3 to the 1 times 5 to the 1, that's 24. That's not 24, that's 60. That is a factor of 1440, but it's not a multiple of 24, right? So not all of the factors of 1440 will still work in this case. And so what I'll do is start by writing out all of the options sort of in this table form as I did in our first example. That's what we have for our first choice, our next choice. Also, I'll say while I'm writing this out that it's just a coincidence that the 2 examples I picked only consist of 2's, 3's, and 5's. You'll see one of the examples that you have to work on as prime factors other than these. Okay, so these are all the options I have for 2's, 3's, and 5's, but note that 24 I can write as 2 cubed times 3. So in order for a factor of 1440 to be a multiple of 24, it has to have at least 3 2's in it and at least 1 3 in it. By that I mean some of these options no longer exist. Right? If it only, say, for example, has a factor of 2 squared, it's not going to be a multiple of 24. Right? It needs to have a factor of 2 cubed, or 8, to be a multiple of 24. At the same time, 3 to the 0 is no longer an option. Right? Because if it doesn't have to have a factor of 3 in it, it's not going to be a multiple of 24. So you can think of this, added condition that, our factors have to be multiples of 24 as restricting the number of options at each stage. So now the number of factors of 1440 that are multiples of 24, well, I still have 3 options here. I still have 2 options here, and I still have 2 options here. And so I'm left with 12. So 12 is the number of factors of 1440 that are multiples of 24. Another way that you could actually think about this problem is divide 1440 by 24. So in this case, 1440, we said is 2 to the 5 times 3 squared times 5. 24 is 2 cubed times 3. Just make sure that's right. Yeah. You can perform this division, and so now I'm left with 2 squared times 3 times 5. And you can just determine the number of factors of what is left over, right? Because you can sort of say, okay, all of the factors that I'm looking at now have to be at least 24. So let me just divide out 24 and determine how many sort of multiples of 24 are factors of 1440. So you'll see that if I compute the number of factors of this thing, I get 2 plus 1, 1 plus 1, 1 plus 1, and that's just 3 times 2 times 2, as I saw over here. And so I get the same result this way. So I could divide out, the sort of baseline that I want. Okay, so that's all that I'll explain in this video, and that should be sufficient to get you through parts A and B. Part C introduces yet another twist, but if you think about sort of the way that we approach the problems in this video, part C is a natural extension of what we did. Okay, good luck and let us know if you have any questions.